Welcome friends, welcome you all in my channel Chemistry the Mystery of Molecules. I am Tanmay. So today we will discuss about Cyanoform. So I suggest you to like, share and subscribe my channel Chemistry the Mystery of Molecules such that you get new videos on a regular basis. So thank you, let's start. So today we are going to learn about Cyanoform. The question, what is the importance to read this molecule? Actually, it's a very recently established molecule, means it is not a very old molecule. So informations are limited, but it has unique property. And that is the reason, that's why I may choose this topic. Secondly, if you ask me that exam perspective, is it important? My question is, I'm not sure. I'm not really sure. Because it's a new molecule, so not predicted that much, but I believe the people who are going to be enrolled for research like CSIR-NET or equivalent type of examination all over the world, so such question could be asked to check whether the candidate really knows the recent discovery and interesting property of molecules. So from that point of view, I guess it will be important. And secondly, throughout this discussion, I shall try to correlate the properties of this molecule with already existing molecule, so you would have a better understanding. So today we will learn mainly about synthesis and the property of this cyanoform, mainly the acidity and its comparison with other haloforms. So let's start. First of all, from the name you can see this molecule is cyanoform, means Tricyanomethane. It has another name, Tricyanomethane. Why? Because this molecule contains 3 cyano groups. So tricyano and it's a methane. The central carbon is sp3 hybridized. Okay, so it's a tetrahedral. So this is the main thing. So the first question is how the molecule could be synthesized. Typically, the molecule is synthesized from this sodium tricyanomethane salt, and hydrolysis in presence of this sodium tricyanomethane in presence of sulfuric acid, and this produces a aqua complex, that is H3O plus CCN thrice minus this. But this doesn't give this tricyanomethane. For that, what people have done, they have taken calcium tricyanoethane, this 2R, and they have treated with HF, more precisely 4HF, to get this cyanoform plus calcium HF2 bifluoride. This is a very interesting, I'll later explain why this HF produces this HF2 type of cation, whether not because of hydrogen bonding. So this is possible. This. And actually this information is a very recently reported research paper I have taken, and that research paper is Angew Chem, or actual name is Angew International Edition, and published in 2017, 56. This is the volume and page number is 9582. So why I am giving this? Because I believe you keep this reference. If you want to read about this one paper recently published 2017, so you can go through the papers, because I guess it is difficult to get information about this molecule in books. Okay. So this molecule reported this synthesis, and what happens when we treated with sulfuric acid and evaporation? Sulfuric acid and evaporation produces this salt. So this is the synthesis part, and right now we will discuss about what is the application of this molecule, that is acidity. So I guess you have understood this is simply a proton exchange process, and why this is formed, because precipitates out. So this is. Now let's discuss about its application. From the structure you can see that one carbon is attached to 3 cyano groups. Okay, so and 3 cyano groups are electron withdrawing. So consequently this withdraws electron, and this proton became more and more delta positive compared to CHCF3 or CHCCl3. This is fluoroform, this is chloroform. This is fluoroform and this is chloroform. You have read it well previously. Okay. So what happens? This molecule easily deprotonates to form this corresponding anion. CN thrice produces H plus and CN minus. One interesting point, during the synthesis you have seen I have taken sodium salt or calcium salt, because this anion is so much stable, this salt could be prepared. That's why this salt is commercially available, sodium salt. So this is the uniqueness of this unique stability. I'll explain. So this is. And in case of the reaction with sulfuric acid, you have observed what is actually produced. This produces H3O plus CCN thrice. Okay, it's a salt. Now, to get more in, before getting the insight, see, it's a carbon ion actually. Cyanide is a group which is covalently attached to carbon, so its charge is balanced. Actually, the negative charge is on carbon, but it is delocalized over cyanide. I'll explain. So it is actually a carbon ion. Okay. Previous in my video I have explained that carbon ions are reactive intermediate. It is very difficult to store them. For example, butyl, lithium, Grignard, even exposure to air it catches fire. This type it reacts with moisture violently. That's why anhydrous solvent, moisture free environment is required for this reaction. But it is also same category, but it is stable because the charge localization. What message I want to give you from this molecule? That it is possible to stabilize a carbocation if proper option, that is electron withdrawing nature, could be provided. So carbon ion could be stabilized if proper electron withdrawing group is attached to it, because carbon is not a high electronegative atom, so it can't stabilize the negative charge on itself by itself. So some delocalization is essential. See, it is a H3O plus is acid. Hydronium ion we consider acid. During workup we write H3O plus, means it's acid. So this carbon ion is stabilized in presence of acid. So this is the uniqueness of this material. Actually we expected that okay, even if we have taken previous synthesis, we have taken sodium salt, okay, sodium salt, then this sodium salt could react with the sulfuric acid and produce that carbon ion. Actually it is not producing, it is producing this. So it is stable in presence of acid also. Okay. So the question, why this is stable? Why this is that much stable? The stability is due to the attachment of 3 cyano group. And how this cyano group helps stabilizing? You know that cyano group has minus I as well as minus R. Okay. So here initially this carbon ion was sp3 when this center is sp3. After deprotonation still sp3, but if it is in sp3 it is not getting any that much stabilization. That's why it changes its hybridization into sp2. And then only it is stabilized. What happens? This p orbital which is filled contains 2 electrons. Okay. This is the symmetry. And delocalizes into the anti-bonding orbital of cyanide. How? Let me draw the anti-bonding. Actually, you also learn how to draw. In this way, it will be easier for you to explain any phenomena using molecular orbital theory. And this is the symmetry of p orbital. One is plus, another minus, and it is arbitrarily chosen. For example, if this is plus, it is an anti-bonding interaction, so this lobe must be minus. Learn this, it will be important. If it is plus, then this lobe will be minus, and if it is plus, this will be definitely minus, this will be plus. So now, right now this symmetry are matching with one another. That's why this will result in bonding interaction. Means actually it's a back bonding of the negative charge on carbon to cyanide. You can compare this story with metal carbonyl or metal cyanide, where this electron on metal is donated in this way to cyanide. So that is, you can correlate, because I guess you have read during organometallic catalysis or 18 electron rule, that part. So think it in that way, it will help you to understand. And this resonance, for example, this CN, this is possible to other also. So in this way, what happens? It gives electron, it comes. So that means this negative charge is delocalized over the entire molecule. That is the reason of exceptional stability of this molecule. Okay? So I guess you have understood why this in spite of being a carbon ion, this group is stabilized. Okay? Oh. So this is its stability, and surprisingly, so generally we delocalize the acidity of a material using the pKa, and generally we say pKa below 1 means a strong acid, and this molecule, this has a pKa around -5, so it is very strong acid. For comparison, pKa of para-toluene sulfonic acid, PTSA. Okay, para-toluene sulfonic acid, its pKa around -2.8. So we can say this is more acidic than PTSA. PTSA is widely used as an acid in organic chemistry, but think that it is stronger than even PTSA. And PTSA is resonance stabilized using this charge here. So in this way, 3 equivalent canonical structure possible. True. Here also 3 equivalent means one donation here, one donation here, one donation here. Actually here 4 structures, resonance structure possible. So this is the reason that's why this tricyanomethane is stable than even or stable carbon ion or more acidic than corresponding this more acidic than this para-toluene sulfonic acid. So this is the unique property of this tricyanomethane. So before going to comparison, I will give another property of this. For example, if we consider carbonyl group, that is this, we know these undergo addition reaction. For example, cyanohydrin addition, HCl. Why I have chosen cyanohydrin? Because it is also a carbon-based nucleophile. So cyanohydrin, what product is produces? The addition reaction OH and Cl. If we take acetone, then the product looks like this. Okay, similarly, if we take acetone and add this tricyanomethane, what happens? It also form an addition product with acetone, and that is this and CN thrice. Understood? This bonding is through this carbon. This proton is going to this oxygen to form this hydroxyl group, and thus carbon ion attacks. So this is similarly like cyanohydride. And this example I have taken that Angew paper, the reference I have given. So okay, now let's do some comparative study. Comparative study, actually you know it's a cyanoform. I am saying it's cyanoform. Cyanoform, you check the name, cyanoform. So, and we know previously fluoroform, chloroform. Okay. So these three. Cyanoform, if we check the acidity, this versus HCF3, HCACl3, its pK around -5, its pK around -25, and chloroform's pK is around 15.7. Sorry, this is not -5. I made a mistake. It's a very strong acid. So 15.7. So you can check. Why? CF has strongest electronegativity, means its strongest electronegative atom, but still only -I effect operates here. I have explained in one of my previous video. I will upload the link below this video, so you can go through that link. I have explained in details. Here -I as well as -R with this chlorine. Okay, and here -I as well as very strong -R, that is delocalization I have just explained. That's why it is more stronger. This is more stronger, after that this, after that this. So keep this thing in mind. You may have some comparison questions using this. And here how -R, the vacant d orbital participation of this chlorine atom stabilizes the carbon ion. That's why this is stable. And second, I'll draw Cl. This is the d orbital. This is the carbon ion. Only one. Minus, plus. This is the d orbital, vacant d orbital. In this way, electron back donation happens. So -I means withdrawn using this bond, and -I means this. So in this way, and second point is that this molecule eliminates one chloride, for example this, and produces Cl2, because this CCl bond is shorter, the CF bond is shorter than CCl. So that's why this elimination possible, and it produces CCl2 carbene radical, which is utilized in Reimer-Tiemann reaction. So I guess you have understood this comparison study with this chloroform, fluoroform and cyanoform. What message I want to give you here? That if strong withdrawing effect, or more precisely strong withdrawing or delocalization by resonance is possible, then it is possible to stabilize the negative charge on carbon itself, similarly like a strong acid, like a derivative of sulfuric acid, that is paratoluene sulfonic acid. So let's discuss another example. Let's give you, for example, if we compare the analogous cyanomethanes, for example, what I mean, HCN, you know, it is hydrocyanic acid. Second is acetonitrile, CN. Then is malononitrile, CN. Then this tricyanomethane. Okay, now we will discuss what is the acidity order and why. For example, now you can see these are all analogous material. So here hydrogen, here CH3, here also added cyano, another cyano. So actually we are checking the effect of increasing of cyano group attached to a carbon, what happens. And this is the simplest example. So if we check the pK is HCN is 12.9, pK acetonitrile around 25, malononitrile around 11, and this around -5. Actually, I suggest you don't memorize these pKa values because this differs. Based on solvent to solvent, some pKa have taken in discussed in water, some in DMSO, these. But for your purpose, it is not that much essential. You need to know only the comparative study, which is stronger, which is weaker. That's why I suggest you never memorize. Even for me also, you may have different values in different, because when I am reading, I have observed that in different cases, different value is mentioned. So it's true that corresponding different experimental condition result in different value. That's why I am suggesting you never try to memorize this value, or based on this value never start any argument. That okay, I know this is right, from there I have read, that's why this is right, I don't accept that you are right. Never do argument because it varies. Okay, this purpose of giving this value to give a comparative study, a qualitative understanding about their properties. Okay, so this is, so what happens here, if we check the corresponding conjugate base is, if means when we are want to describe about acidity, we should check the stability of conjugate base. In this way it is easier to understand. Conjugate base is cyanide minus. Okay, here acetonitrile's conjugate base is CH2 minus, because proton is eliminated from here, so CH2, C triple bond N. Here malononitrile minus here and attached to 2 cyano. Another here three cyano. Okay, now you have to check how it's getting stabilized. This is simple cyanide anion. These don't have any resonance stability, but due to the attachment of this electronegative nitrogen, and second point is this is in sp hybridization, so charge remains closer to carbon, that's why it is stabilized. How this is stabilized? This is stabilized by one canonical structure. What? CH2 double bond C double bond N negative. So in this way it is stabilized, but this stabilization is not that much instant. So in case of this next one, this anion is stabilized by these two sides, means resonance is possible from both sides, this side as well as this side. So its stability more pK I explained previously. So this is the reason. So this indicates that increasing the extent of resonance or delocalization, acidity affects. So that's why from this to 11 to -5, this much shifting is possible. Okay, and this malononitrile is a very important synthetic reagent, and you should know. You know, because this active methylene group is a very important thing in this chemistry or in exam perspective. It is also very important thing. So last, before ending this video, I will give you an example of industrial process for preparation of this tricyanomethan or cyanoform. Actually, I have told previously that it is prepared from sodium salt. Question: from where sodium salt is coming? But compared to that, what is the most important question? Why I am giving this information at the end? Because previously I told that this is not a well-established textbook chemistry that you know everything. So I thought, since it's an industrial process and I have collected this from a patent, so I don't know that much information. It is not available. It is a closed document. So that's why I thought that give you very small information, but at that end. What is? That is this malononitrile. This malononitrile, just I have explained, plus chloro means cyanogen chloride. Keep the name in mind, cyanogen chloride. Similarly, cyanogen bromide also available, where this chlorine is replaced by bromide. In presence of NaOH, it produces this sodium salt. Minus Na plus sodium chloride plus water. Okay. So what is unique here? You can see this is acidic, pK around 11 something. I have explained just before. So what happens first? It abstracted proton to prepare this Cn, and then this is resonance stabilized, and this attacks to this Cn, because previously, don't get confused, when we write cyanide as a ligand, we wrote that this is minus and we say that this negative charge over carbonate is true. But when it is attached to cyanide, then this carbon is delta positive because attaching electronegative atom. Even if you check this hydride or alkyl lithium, they attack here like carbonyl group and produces double bond or means partial reduced or completely reduced product. So this is electron deficient. Never confuse this with cyanide. Okay. So these attacks here. First happen nucleophilic attack. This electron goes here and again it push and chlorine goes out. What is produced? Cn, Cn, Cn. And corresponding sodium is countercation. So we got our targeted product here. So this is the way to prepare. Now one question could be given. It's an interesting thing. So the question is, here we are using two equivalent. Actually I should mention here, it's a two equivalent sodium hydroxide. First equivalent needed deprotonate. First equivalent we needed for this deprotonation, and second equivalent we needed deprotonation here. I made a mistake. Sorry, I made a mistake. That's why I am confused. This Cn negative charge reacts with cyanogen chloride to produces not directly the salt. Initially it produces another intermediate, tricyano. This is it produces, and it also contains one proton, but this is a very acidic proton, pK around -5, like acid. So instantly it react with sodium hydroxide to produce water and the sodium salt. Okay, that I confused. So this is the main theory. Now the question is, if instead of two equivalent, if we provide one equivalent, what will be the product? That's the trick. So if we provide one equivalent, so initially some molecules of hydroxide will react with this to produce this. Okay, and after that, here two reactions are acid-base reaction, and both are carbanion generation. But here we are generating a carbanion attached to 2 cyano, and here we are generating a carbanion attached to 3 cyano. So this is the difference. Means this carbanion is more stable compared to this because of the pK value. You know 11 versus -5, extremely different. So 2 cyano, 3 cyano. So at that time it will be produced, instantly converted into this one, sodium salt. So ultimately what will be the product? Means it will be, if we take this one equivalent and one equivalent, so we get 0.5 equivalent sodium salt, and the rest of malononitrile will remain unreacted. This is the trick. Keep it in mind. Okay. So in this way you can solve question. I guess you have understood the part. So if you like my videos, please give a thumbs up and share this video among your friends, and subscribe my channel Chemistry and History of Molecules, and finally press the bell icon to get the notification of every single video I upload. Thank you. See you in my next video.